Okay then guys, I think this is about the sixth video on rates. Rates is a complicated and big topic at A2 Chemistry. It's not something that you have to really get stuck into. You have to do lots of questions, and if you can do as many questions and have as many techniques, it's not a problem, but you're guaranteed to get rates on the paper and you're guaranteed to get a lot of marks on the rates. It's a big deal, okay? So, I'm going to do now, I think this is, like I said, the sixth one, graphs and rates. Now, graphs is a big part. Interpreting the shapes of graphs and getting information from graphs is the second big part of doing rates. So far, we've looked at not so much the graphs, we've looked at the experimental data. Okay. Now, I've already met graphs to a certain extent. So far. Okay, where have we got to? Well, we've looked at monitoring the progress of a reaction by having a quantity that is observable, that is measurable. Colour maybe against time. Colour, that will come right against time. Two of these, two possibilities. Quantity against time. Right, so your quantity can be mass loss. Volume of a gas. I'm repeating myself here, it can be colour or pH, anything that can be continually monitored. Okay, and you end up with, say, if it's, say, volume of a gas, it'll do that. Okay, if it's mass loss, it'll do that. The reaction will do that. That gives you a way to continuously monitor the progress of the reaction. That, of course, gives you a way to do a gradient, an initial rate gradient, or in fact, a gradient anywhere. At AS, they might say the rate after 0, the initial rate, which is the one which is by far the most important. But you can take a rate, you can take a tangent at anywhere on that graph, and you can do the rate at any particular point in time. Okay, and the rate will decrease by doing the gradient of that tangent, or doing the gradient of that tangent, or any tangent along that curve. Likewise with this, you can do the gradient there. You can do the gradient there. And it'll give you a negative gradient, but it's a value of the rate. Ignore the fact it's negative. So that will give you t equals 0, your initial rate, or here, whatever time that is. Okay, so that'll give you the rate. But we need to standardise these. What I mean is, if you look at what you need to do at A level, at A2, is you sort of monitoring, you're able to do some maths and monitor from these quantities how a concentration changes as the reaction proceeds of a reactant. And that's how we look at these graphs, how the concentration of a reactant changes. Those graphs will work out the rate. This is a bit tricky to get your head around, but it's actually straightforward. You can produce a set of graphs which specifically look how the concentration of a reactant within the rate equation changes as the reactant proceeds. Okay, and you can work these out from other measurable quantities, how they change with a bit of maths. But I'm skipping over that because I want to get to the meat of it, right? So what we're saying is monitor the concentration of a reactant. Decreasing over time. It's a sort of a projection of these, okay, is one way to put it. Now, reactant will decrease over time as it gets used up in the experiment, and you will get a shape how that concentration changes. So the first set are called concentration time graphs, and you must look at the axes for these because I'll do another set. There's 3 of these and then there's 3 of another set, and you've got to make sure you know what's what, and you've got to make sure you look at the axes so you don't get mixed up and confused. Okay, so I'll put a thing around now. Okay, right. Here we go. There's 3. 1, 2, 3. And they're all going to look like this. Concentration of a reactant, let's call it X, against time. How does that change as the reaction proceeds? These can be deduced from experimental data. And we'll do a practical to show a few ways of doing that. But that's not something to worry about too much. 3 graphs. Concentration time graphs. Okay. What about if you measure the concentration of one of the reactants as the reaction proceeds and you end up with a graph that looks like that? Straight, but at a sort of declining angle. What that means is that the reaction is 0 order with respect to concentration of X. So X is being used up as the reaction proceeds, but if you get a graph of line of that shape, it is 0 order. It doesn't matter what the concentration of that reactant is. It does not affect the overall rate. So it's a straight graph going down, but with a sort of a sloping gradient, if that's the right word. You see that, you know it's 0 order. So it's something that they could put there so you don't have to deduce the data. You know it's 0 order if they give you that. Okay? Again, the questions are all with this. Okay, this is an overview of the concepts. Now this one is quite important. I'm going to have to be careful how I draw this and compare to this one as well. So, does this. There is your initial concentration, right there, your starting concentration, and the concentration goes down as the reaction proceeds. It looks like this, so be very careful how I draw this. Okay? A curve going down like that. I haven't drawn it brilliantly, but it's okay. Then you look at this one, and the reason I'm doing this is because the shapes of these look very similar, but this one is much sort of tighter to the axes. It sort of does that. It sort of drops more rapidly and then sort of narrows out like that. Not quite the same. Not quite the same to look at, and not quite the same. If you get one, so what do they mean? Well, if you get one that looks like this, the reaction is first order with respect to concentration of X. If you get one like that, it's tighter in, it's more of a dramatic drop. Reaction is second order with respect to concentration of X. And you might say, how do you tell them? How do you tell? Because they look a bit similar. Right, and these are A-level questions. How do you, what can you can get a lot of information from these graphs, a huge amount. Okay, so this one, you can do a gradient at the initial concentration, right, a gradient there. The gradient there, a gradient there is the rate, the initial rate. So you can get the rate. If you've got a graph of that information, you can draw a tangent, you can work out the gradient, you've got the initial rate. You can also, but this isn't asked very much, if you have that, you can do exactly the same there. Tangent, you can calculate the rate at any point in time along that curve. No problem. Okay? Exactly the same with this. You can calculate the rate, the initial rate, this isn't asked very much, by the gradient. Equals initial rate. Again, in theory, I've never seen this asked, you can calculate the rate at any time, at any particular point in time as that reaction proceeds. That's one thing you can do, work out the rate. Okay, that might be very important. Okay, What else? Well, you can decide what the order is. So let's say, for example, the initial concentration of, you can actually say, because these are, like I say, quite similar, you can be clear that this is first order, and you're going to have to, and that this is second order. How do you do that? Well, let's say your initial concentration of X is, I don't know, 4 moles per dm cubed. These are in moles per dm cubed, of course. And let's say you take a tangent there, and you work out the gradient, and let's say the rate is, I don't know, 2 times 10 to the minus 3. Then you go down to half the concentration, 2, and you do a tangent there. Okay, and you work out the gradient of that, 4 to 2, half. Okay, rate, if it's first order, should be half. So by taking 2 points, one half of the other, and working the rate out at those 2 points, you can tell that that is first order. If the concentration's gone down by half and the rate's gone down by half, you've got a first order. You've got a first order reactant there, essentially. Okay, so you can do 2 gradients, 1 half the concentration of the other. If the rate is half, you've got a first order reaction on your hands. Okay? The other thing you can do is something called constant half-life with a graph like this, both of which, the question in the exam will be, use the graph to deduce the order of the reaction. Okay? So, with respect to this particular reactant. Okay, now the other thing you can do, and again on a video this isn't easy, it's certainly something you have to do in the exam, it's something called constant half-life. They love this. To prove that it's first order, to confirm it's first order. And what do you do for that, right? Well, you take 2 values on this axis, right? And you have a time. That's going to be 0. 2, so 4 and 2. Then you go down to your time axis. Let's say it's taken 10 seconds. Okay? Then 10 seconds to go from 4 to 2. That distance, 10 seconds. Then you go down by half again. 2 to 1. You go along to 1. You go to the line. You go down. Now, if that is a first order shape, the half-life is constant. In other words, to go from 4 to 2 moles per dm cubed, right? If when the concentration goes down by half, it's taken 10 seconds. Do a second half-life. The time for the concentration to go down by half again, from 2 to 1. If it's first order, it should, with an experimental error, you're going to have to get your rulers out and you have to show the examiner you're doing it. It should take, near examine, 10 seconds. And if you were to do a third for confirmation, you go down to 0.5 moles per, so you're going down there. So from 1, 20, that should be 30. Another 10 seconds. That is what we mean by constant half-life, and you will be expected to show on a graph that is given to you, normally with graph paper on it, so that you can get it absolutely spot on, rather than this, which is a bit hit and miss. This tells you that the half-life is constant, the order is first order with respect to X. Okay, so you can not only get the rate, you can get the order as well with respect to that. So there's a lot going on there. Okay. this is a big deal, right? So in fact, if that's the only reactant, okay, then you can deduce that you can deduce the rate equation for this. If this is anything you're given, maybe you give another data for other reactants, maybe not. But if you're not, you can deduce that the rate equation is K X 1. Okay, and right, you can work out the rate there. Okay, and that's the initial rate. You can for that initial concentration. Okay, put the numbers in. So initial rate, initial concentration. Okay. So if I take my numbers here, right, at 4, the rate is that. You can deduce, you can work out K from this as well, because taking my numbers, the initial rate is 2.2 times 10 to the minus 3 equals K, first order, which you've deduced as well, initial rate, initial concentration, times 4. So K is equal to 2.0 times 10 to the minus 3 divided by 4. What I'm trying to say is, and you know, again, it's all about doing the questions and practicing this. A first order reaction like that, or given a graph of that shape, there's loads of things that you can do to work out a lot of stuff on that, just from the shape of that graph. Second order is less common. But I suppose second order you can do exactly the same. It will not, no constant half-life. It won't work. These are much less common because these are sort of negative, finding out that something isn't first order, whereas they tend to ask that it is first order. So no constant half-life. If it's second order, it's going to be tighter in, and you're going to have no constant half-life. It's going to be second order. Okay? But in theory, so if it's second order, a shape like that, no constant half-life, you do a bit of a half-life on it and it's all over the place, you can come up with this conclusion if it's only the reactant. These are, right, you can say that. So if you were to do a rate here, initial rate, and let's say that was 4 again, right, you could work out the initial rate, plug the numbers in based on 4 initial rate, work out the rate constant for that graph. Lots that you can do. Okay? So those are concentration time graphs. Those are a big deal. How much longer have I had? 18 minutes. So, yeah, quite a nice little summary for you there. No problem. Nothing else to say. Okay. Half-life. I was looking through some... Oh, no, I won't do that now. Right. Now, there is another set of 3 graphs. I have to say, probably in terms of being able to manipulate this concentration time graph first order is massively asked. But let's have a look at the remaining 3 on this video. So, gone. And really, that should be gone as well. Let's have a look at the second set of 3 graphs, and these are called rate concentration of X graphs. Right? Now, same deal. They're not the same, they are totally different, and they'll try and catch you out in the exam to see whether you've learned them, and give you little multiple choices on these. Okay, right, rate, concentration of X as the reaction proceeds. Okay, you're going to get this. As the rate, as the concentration of this gets used up, as the experiment proceeds, the rate is unchanged. Straight line like that, that's what you would expect. In other words, 0 order with respect to X concentration. As that concentration changes, increases, decreases, whatever, the rate stays the same. Okay? Right, this one. Rate. I suppose at any particular concentration, you've got the value of rate there. You don't have to work out anything. There's no tangents to be drawn in this sequence of graphs. It's already there for you. So this one, concentration of X increases. You should be able to deduce this yourself. First order with respect to concentration of X. What shape are you going to get for that? Answer, it's one of those, what mathematicians will call it, a proportional relationship, or whatever you want to call it. You get a shape that looks like this if it's first order for X. Straight into the origin, straight like that. Okay. Now, while I'm on it, we've never looked at temperature. Temperature has never been part of any of this rate stuff. It's all about concentration. And there is a bit on temperature which I'll come to later. But let's say that the temperature of that is T1. What shape would you get if you did the experiment and it was exactly the same reactant and exactly the same concentration of reactant, first order, but you did the whole experiment at a high temperature, still first order, same shape. T2 would just be angled up more at a higher temperature. Okay, that's a bit unusual, but that did come up. Now, what can you glean from that? Rate is equal to K, concentration of X, first order. Right, so you can deduce the whole of this. There might be other evidence for other reactants. Okay, you might just get completely graphical evidence. So you might have Y, 0 order, X, first order, and maybe Z, second order. And you can use this to deduce the whole thing in a way because, right, here we have rate, okay, so you can take any points you like. There's no tangents to be drawn. So whatever concentration you want, you can find out the rate for it, okay? So let's say that the concentration is 5 moles per dm cubed at that point and the rate is 2 times 10 to the minus 4. You can bang those numbers in. Times 5. Okay. So everything can be done with that. Work out K. Anything else to say about that? I don't think so. Finally, second order, right? Concentration. Very different shape. Because it's a squared relationship, you get a shape of the graph that looks like this. Bang on second order with respect to X, if you get a shape like that. Sort of angles up. So you can say this, right? If this is the only reactant, equals K, second order. So you don't get this asked very much, but in theory, you can work out the rate constant from that, no problem. Just take a concentration, exactly the same as we did over there, 5, say. Right? Track back to what the rate is, I don't know, 2, same deal, 2.0 times 10 to the minus 4, whatever the numbers are. So it's all there for you on a graph like this, okay? And then you can put the numbers in. So K, you can calculate the rate constant, no problem, is equal to the rate, 2.0. You don't have to do the initial well, as the concentration decreases. Anyway, you can do this any way you like on here. So what we've got, shove the numbers in. K is equal to the rate, 2 times 10 to the minus 4, divided by concentration at that particular rate, 5 squared. So you can work out the rate constant based on a graph like that. Now I've covered every eventuality with those graphs as far as I'm aware. Okay, this is gives you an idea, well, more than an idea, it tells you exactly of the sort of things graphs. Okay, but again, practice makes perfect. These graphs are all over the papers, and they'll ask you to deduce, maybe do a tangent and then a gradient to calculate the rate. They'll ask you to deduce if it's first order by looking at a constant half-life. They might even ask you to calculate K. Lots of things that you can do with those graphs, or there might be a number of reactants and it just gives you the graph for each and say, okay, deduce the rate equation based on the shapes of these graphs. So you can do as much with these graphs as you can with the raw data that we've looked at earlier. Now, let's say raw data questions that we've been looking at in some detail, 60%. Graphs to deduce orders and stuff like that, 30%. The remaining 10% is, I'll come on to, are really experimental things and mechanisms as well. Okay, so that's an overview, but there's no substitute, like I say, for doing as many questions on this as you can, and you'll find it all fit together if you do that. Okay, all right then, guys. How long have I been on here for? Long enough. Okay, I'll see you later.